Now, why are conservation biologists interested in this? Well, if a population is out of Hardy-Weinberg equilibrium, it means that there is an evolutionary force that's working on the population to keep it out of equilibrium. And Jed mentioned some of those forces. Those include very small population sizes where genetic drift can affect these frequencies. There's mutations, there's random mating or non-random mating, there is natural selection, and there's also gene flow. And we'll talk about all of these different forces in different videos. But when you see a population is out of Hardy-Weinberg, then it gives you good evidence that something is happening to keep those individuals or to keep that population out of the distribution that we expect. If the population were randomly mating, there were no mutations, there's no drift, etc., etc. If our population is out of Hardy-Weinberg, how many generations do you think it would take to return the population to Hardy-Weinberg equilibrium? That is, if we removed any of these evolutionary forces that might be keeping this population out of Hardy-Weinberg equilibrium. And just to throw an example here, what if this population was all A1, A2 heterozygotes because natural selection favored those genotypes and the A1, A1 homozygotes and the A2, A2 homozygotes were selected against? If we removed that pressure from the population then and let these individuals mate at random, how long do you think it would take before the offspring population returns to equilibrium? Well, let's find out. Here we've set up a sort of a corny simulation where we're going to let these individuals each reproduce. And we're going to give them a gamete down column C. Then we'll choose a random parent, a random mom, and return her gamete from the egg. And we'll also choose a random dad and return the gamete associated with his sperm. And then we'll join the egg and the sperm to create the offspring genotype. Now, to generate a gamete, we're going to take a random number, and if the random number is less than 0.5, we're going to assign the allele that's listed on the left side of the genotype. And if not, we'll have the spreadsheet return the right side of the genotype. And we'll do this with an if function. So our logical test is if a random number is less than 0.5, and this, by the way, is simulating the process of meiosis, more or less. So if a random number is less than 0.5, then we'll have the spreadsheet return the left two characters that are listed in cell B9. And there is a function in Excel called left, and we'll enter B9, and then we'll place a comma, and the second argument is the number 2. So this is telling Excel, return the left two characters of whatever is stored in cell B9. And if it's false, we're going to have Excel return the right two characters from whatever is stored in B9. And we press OK, and then copy that through, and we have a gamete for each individual. Now to choose a random mom, we're going to enter the word ran between. And the bottom number is 0 and the top number is 999. That's because our individuals are numbered 0 through 999. And we can do the same thing for the dad. Ran between. The bottom number is 0 and the top is 999. Now we need to find the random mom and return the gamete that is associated with her. Likewise, we'll find the random dad and return the gamete that is associated with him. Now, in reality, this is a very, very simplified situation in which individuals produce just one kind of gamete. And also, you might have noticed is that individuals can occur in this list more than one time, and it is possible that we draw the same random mom and the same random dad as the same individual. So we're really dealing with an organism here that can produce both eggs and sperm. That's not a big issue. We're trying to make a point here about how quickly we can get back to Hardy-Weinberg equilibrium, so let's just press on. To find the gamete associated with the randomly selected mom, we're going to use a VLOOKUP function. And this function has 4 arguments. We want to look up the random mom, which is stored in cell D9, in a table. And our table is going to stretch from column A to column C. A key here is that this V stands for vertical. And so the number that we are searching for needs to be in the left-hand column of our table. We'll select all of our cells, and let's go ahead and anchor this reference to the table itself. And when Excel finds the number it's looking for, we want to return the value stored in the first, second, third column. And because we want an exact match, we'll enter the word false here. So this process is generating a random parent and the gamete that they have. We want to use the same equation for the dad, so we can just copy this equation and paste it in. And this time, though, we want to look up the random dad in this table and once again return the third column. And you can see here that the offspring are generated as by just joining the egg and the sperm. This symbol right here is an ampersand, and this is also called the concatenate function in Excel. Now at this point we have the offspring genotype, and we can calculate the observed number of these different genotypes in these cells here. From here we can calculate the frequency of the A1 allele in the offspring population and the frequency of the A2 allele in the offspring population. And I've designated that as F1 for the next generation. So you'll want to fill those in. What I'd like you to do is to use the same general equations we've used up here for the parental population and go ahead and enter them into the offspring population. And then we'll turn your video back on after these calculations have been done, and we'll compare our results. So we'll see you in just a few minutes. How'd you do? Well, hopefully you got some results that look something like mine. Let's just review where we've been. We simulated a population that was totally out of Hardy-Weinberg equilibrium, and then we let them mate at random. We had no evolutionary natural selection happening in this population. There was random mating. The population size was very large, 1,000 individuals. There was no gene flow. There was no mutation. In other words, there were no evolutionary forces working on this population. So when they reproduced at random and generated offspring, we compute the observed number of each of these genotypes in the offspring population, and we then compute the frequency of the A1 and A2 alleles in the offspring population. We see that our offspring population is back in Hardy-Weinberg equilibrium as predicted. Let's head back over to JED now, and we'll review some of the more fundamental concepts of the Hardy-Weinberg principle. And for now, just keep in mind that this is the most basic test of whether a population is undergoing some kind of evolutionary change.
Great, thank you, Terry. I hope that exercise was helpful in terms of understanding the mechanics of how to calculate things like genotype and allele frequencies, and really in terms of demonstrating how the Hardy-Weinberg principle actually works. So we've covered a fair amount of ground here. Let me just recap some of the main points of what we've covered in this module. For one, the Hardy-Weinberg principle is really one of the foundations of the genetic theory of evolution. And it basically states that when a population is large and that its individuals are mating at random and there's no mutation or migration or natural selection occurring, that the genotype frequencies should remain constant from one generation to the next. So those constant genotypes then we refer to as being in an equilibrium state. So the population is in an equilibrium state. And what that basically means is that the population will not evolve because it's not facing any sorts of evolutionary pressures. And because of that, the Hardy-Weinberg principle is oftentimes referred to as the null model of evolution. If we see some violation of the assumptions of Hardy-Weinberg, then we can conclude that there's some sort of pressure, some sort of disturbance, some sort of stress that's affecting this population, and that it may indeed be evolving. So the Hardy-Weinberg principle gives us a means of assessing the state of a population, and that has some merit in terms of how we structure the way we manage or we conserve populations. So at this point, I hope you've got a good solid understanding of what the Hardy-Weinberg principle is, and again, why it's relevant to species conservation and management.